Okay. So, one other way of doing the same type of analogy is basically if you look at, so your tau naught is basically your mu plus rho epsilon m to du bar by dy, okay, and q naught double bar is k plus rho epsilon h into Cp dt bar by dy. Okay. So, these are the two expressions. Now, if your Prandtl number is of the order 1, that is equal to 1, and your epsilon m and epsilon h are the same. Okay. So, therefore, what you have is basically tau naught by q naught double prime is equal to mu plus rho Cm k plus rho epsilon h into Cp du bar by dy dt bar by dy. Okay. Or in other words, so I am not writing the left hand side anymore, I will write the right hand side, rho Cp plus rho epsilon m divided by rho Cp divided by k rho Cp plus rho epsilon h Cp divided by rho Cp. So, du bar by dy divided by dt bar by dy. Okay. So, again this part I am not writing, I am only going to work on this particular section, and therefore, we show Cp divided by alpha plus epsilon h. Once again this part you can see what we are going to write. This part I am not writing anymore, minus, so tau naught divided by q naught square, q naught double prime is equal to 1 by Cp du bar by dt bar, right. So, in other words, as you can see over here, Prandtl number is equal to 1 and epsilon m is equal to epsilon h, right. Based on those assumptions you get this as your final form. Now, if you integrate this, integrate from the wall, which is basically u bar equal to 0 comma t bar is equal to t naught to u bar equal to u infinity, t bar equal to t infinity. If you integrate across those two limits, okay, what you are going to get is t naught minus q naught double prime Cp divided by t infinity minus t naught is equal to u infinity. We already know that Cfx is basically tau naught divided by half rho u infinity square, right, and your Stanton number is basically h by rho Cp into u infinity. So, combining these two, we get half Cfx is equal to Stanton number. So, you basically get the same thing for Prandtl number is equal to 1. Okay. This is also the Colburn analogy, and it also is for Prandtl number t is equal to 1. So, in other words, what this essentially means is that from that expression that each eddy okay, has the same propensity to transfer heat or momentum for Prandtl number, the turbulent Prandtl number is equal to 1. Okay. So, when this is not equal to 1, this expression starts to deviate. Okay. That is, it starts to deviate from the Colburn's analogy that we have over there, right. So, now that we have come to this particular form. Okay. So, let us look at some of the one interesting way of putting things together. That means, if you have, say for example, this is like a flat plate, this is the boundary layer profile, and if you take a look at any particular section of this boundary layer profile, any particular section. So, this part is x, this part is say x1. So, what we can say, because of the nature of turbulence, that is because it is highly oscillating. So, each spot, so far we have done assuming that is nice and steady, right. Another way of approaching the problem is that to have some temporal fluctuations, right. Right now we have said that it is all nice and steady, our equations did not have any temporal variation at all, right. So, one way, this is of course done by Bejan in his book, that each spot of this wall is contacted. So, I am just writing the basic features, contacted by u infinity, which is a fast moving fluid, and T infinity, which is a cold fluid. So, when they are contacted, each spot of this wall is contacted by this fast moving and cold fluid. Therefore, it is characterized by max shear stress or heat flux. So, whenever that happens, it is characterized by the max shear stress and heat flux, right. In a way that is true, because you are bringing in all of a sudden fast moving fluid and cold fluid, right, when each spot of this wall, right, in between being covered, in between the regions are covered with slow and hot fluid, right. And so, in between these things you are met with this slow and hot fluid. So, if you transfer it to a graph, I think that will be visually appealing, that this is the say x and x1, these are the, I am only looking at that part of the box, right. So, what happens is that this is basically your kind of your tau naught max, right. So, what happens is that this is basically your tau naught wall, tau naught x, the some kind of a average quantity. So, you see that it goes up like this, it comes, then it goes up, and then again something like this. So, it reaches up to that particular level, and each of these coverage areas is given by L. So, basically this is the time averaged quantities, which is basically tau naught x and q naught double prime x. So, both of these are basically time averaged quantities. So, now and tau naught t and q naught double naught t will vary in that length scale, which is x to x1, right. So, that is the emphasis. Now, let us now say this neta as a function of x is equal to L, which is the direct contact spots divided by the total length of sample wall x to x1. Okay. So, this is the total number of those contacts. What is the sum, and this is the total length, because some spots are never really wetted by this cold or hot fluid, okay, cold fluid essentially. Okay. So, therefore, your tau naught divided by tau naught max, okay, should be a function of this neta, and this should be similar for this your q naught and q naught double prime max. Okay. Got it? So, now therefore, your tau naught by q naught double prime therefore should scale as your tau max by q double max. Okay. So, when there is a hot momentum, when there is a cold fluid coming hitting at a fast pace, it is also bringing cold temperature with it. Okay. So, that is why this scaling actually works. So, this we already know, this is of course Stanton number divided by half of Cfx. So, this actually then varies as q double prime max divided by T naught minus T infinity into u infinity divided by Cp tau naught max. Okay. So, what are the scales basically? Scales of tau naught max and q double prime 0 max. Okay. So, tau 0 max scales as rho u infinity square into u infinity L divided by gamma raised to the power of minus half. This comes from your laminar boundary layer theory, if you recall, right? Okay, because that is what the cold is actually meeting the surface. So, then q double prime max divided by T naught minus T infinity therefore scales as k by L Prandtl number 1/3 u infinity L by gamma raised to the power of half. All these are valid for Prandtl number greater than 1. Okay. So, for this laminar sublayer that covers the direct contact spots, this is like a flat plate with length L in the laminar shear layer. That is what we have used over here, right. So, Stanton number x to half Cfx is therefore equal to KL Prandtl number 1/3 u infinity L by gamma raised to the power of half rho u infinity square L by gamma raised to the power of half multiplied by u infinity T naught minus T infinity into 1 by Cp. This therefore, if you do all the motions, this will be Prandtl number 2/3 into 1 minus T naught minus T infinity. This is very similar to the Colburn. You just do the math, do the steps, you will get this Colburn formula. Very, very similar to the Colburn formula. Okay. Also, we get your neta actually equal to Cfx divided by u infinity L by gamma raised to the power of minus half. This is also you get. Okay. Okay. So, we got a lot of detailed outcome for the temperatures, okay, and we also got a lot of detailed insights, okay, into the external flow, right. For the turbulent external flow, we can summarize and say that there is an outer region, right, then there is an inner region. Inner region is composed of two viscous sublayer and the turbulent sublayer, right. In the viscous sublayer, okay, ends where the Reynolds number is approximately 100, okay, then the turbulent sublayer is marked by small eddies. Okay, we have established the analogy, okay, between heat and mass transfer. Okay, for the temperature profile, there exists something called CSL, which is basically conduction, which is basically the same as the viscous sublayer. So, conduction sublayer. This is of the order of 11.6, this is of the order of 13.2, right. In addition, we have learned something about Prandtl mixing length, the closure problem of turbulence, right, and where it originates. We learned that it is the nonlinear terms in Navier-Stokes equation that were responsible for the for u prime v prime and then u prime t prime v prime t prime, etc. Okay. We saw that the boundary layer approximation is valid. That means you still have your dy much greater than your dx, right. Got it? Huh? So, there are numerous such things that we have found out, okay, using a lot of these relationships. Got it? Okay. So, the closure problem of turbulence and the Prandtl mixing length, everything we have been able to provide, analogy between heat and mass transfer, the inner region, the outer region. So, we have covered a lot of materials, okay, especially in the external flow part. Now, what we are going to do is that we are going to look at the turbulent duct flow, right, because turbulent duct flow is the one that is going to take us to the almost towards the end of this particular lecture. Okay. I mean, let us start with the turbulent duct flow and let us see how much we can do in this class. So, turbulent duct flow is a typical example of an internal flow, right. So, you consider this as your duct. So, this is your R, this is your X, this is U bar, this is your V bar. So, I am not going to redraw it once again. This is what we are going to carry forward in the next class also. So, again we are trying to do the same thing like Rand's approach. That means we are doing the Reynolds averaged Navier-Stokes equation. Okay. So, for this particular duct, what we have, the equations are is equal to 0. That is the continuity for u. Okay. Similarly, okay. So, it is observed is observed that the turbulent flow becomes statistically fully developed. Okay, so that means hydrodynamically plus thermally, okay, after x by d of approximately 10, which is basically the same as xt by d. Okay, one is the thermal boundary layer thickness, one is the velocity boundary layer thickness. Okay, so these are the basic equations. It is observed that it becomes statistically fully developed. It does not mean that all the fluctuations are gone. It is statistically fully developed, and on the top of that, no wake region, and of course inertia is negligible. No wake region and inertia is negligible. Okay, so this is r and x, this is u and v, u bar and v bar rather. Okay, and so this is the expression that we have. Okay, so we will do a force balance now. So if this is the pipe or duct, whatever, we take a control volume along this. So this has got the pressure P. Okay, so there is the pressure on the other side, which is basically your P bar plus dP bar. Okay, so this is the center line, this is at R naught, that is that, this is x, this is x plus dx, right. So what you have, if you do a force balance on this, right, you will have your P bar into pi R naught square minus P bar plus dP bar, okay, pi R naught square minus tau naught into 2 pi r dx is equal to 0, right. Of course, you have the shear which is acting here, that is your tau naught, right. So this is just a control volume. Around the control volume, what are the forces that are applicable? You take that there is no inertia, so there is no component of inertia that is acting, so it is only a pressure and the shear stress balance, right. So therefore, what you get is minus dP bar by dx is equal to 2 tau naught by r naught. This is quite clear, right. This is how you get it. So this solves a major part of the problem, because if you look at your previous expression, you find that this term is obviously not really useful, right, because that is inertia. We needed something for dP by dx, right. We needed to know what is the nature of dP by dx. Now we have found out what will be the value of this dP by dx. So that is nothing but the wall shear stress. So therefore, 2 by rho tau naught by r naught plus 1 r d by dr okay. We have just substituted for dP by dx, that is all that we did, took it and substituted here, right. Okay. So this forms the basis. Now we can quickly do the integration. So r gamma plus epsilon m dr is equal to minus 2 by rho tau naught by r naught r square by 2 plus c. Okay. So at r equal to 0, dur by dr is equal to 0. So therefore this leads to c is equal to 0, right. So, together what we get is gamma plus epsilon m du bar by dr is actually equal to 1 over rho tau naught r by r naught. Okay. So, that we get through our standard because this r and this r, one r cancels out. So, this is the form that we get, and this 2 and this 2 cancels out. So, this is the form that we get. Okay. So, out of this, this we already know is a tau apparent. This is the apparent shear stress. Got it? This is the apparent shear stress, and on the right hand side we have the actual wall shear stress, the wall shear, right. So, in the next class we will see how we can handle this problem from this part onwards, right. So, this is very easy. We have now got the apparent shear stress is equal to the wall shear stress multiplied by these factors. Okay. So, we will do in the next class that how this problem now can be handled. Thank you.